All right, let's begin then. My name is Raheel, and I'm going to talk about machine learning and how machine learning can be used to tailor games better towards your players, towards player profiles. So I,
Speak up, or is there a mic or something?
yeah, I'm not sure if it's on. Okay, then I'll,
No, the podium, yes.
yeah, yeah, I think that doesn't work. Hello, hello. All right, I'll just speak up then. Thank you. All right, my name is Raheel, and I am going to talk about machine learning and how it can be used to tailor your in-game content towards the players in a better way. I have been working in the game industry for about 6-7 years now, and about 2 years ago I discovered machine learning and how it can be used to improve games. My focus is HTML5 games and mobile games, and that's what I do at Flying Sheep Studios. We are a small but diverse team, and we are based in Cologne, Germany, and we do mostly work for hire and some of our own projects as well. And our focus is making games or web games that are as good as native mobile games, because that's still a challenge, but the WebGL platform has gotten to a level that you can at least try to mimic some of the quality or the resources that native mobile gives you. So before I begin, I first want to let you know that I am from entertainment industry, and the games that I have created so far are usually for entertainment. And although my company does sometimes gets contracted to make games that are for a younger audience, so like 2, 3, or 4-year-olds that have no concept of language or reading or comprehension yet, and we have to make sort of a toy that educates them for stuff like safety and so on. But still, I would say that I am in no way an expert of or in the serious game industry. But the topic that I'm going to talk about today is something that's generic enough that can be replicated and used in any sort of game possible, or even any app possible. So yeah, before I go any further, I just want to give you a bit of a spoiler, because I understand that the title of the talk is a bit vague, since machine learning can be used to solve all sorts of problems. So I'm going to talk about a specific type of machine learning algorithms, a special breed called recommender systems. What recommender systems do is they, on the one hand, take items as input. So these can be anything. These could be items in your in-game shop. These could be exercises in your educational game. These could be levels in your puzzle game, and so on. So on one hand, it takes note of what items there are in an application. And on the other hand, it tries to learn about users. And it tries to create as much as of an in-depth profile of a user that it can. And once it has these two things, then it tries to match items with the users. So which items are suited for which users? Now, the concept of recommender systems is pretty common. Even if you haven't heard the term so far, you have experienced these in one way or the other. So for example, Netflix or any video streaming websites, they make your user profile and then they recommend stuff that you would like to watch. That's one. Another one is social media. So you might have noticed that Facebook or Twitter changes the feed and curates it based on your preferences. And online stores do that in a very obvious way. So if you go to Amazon and you even think of buying a toaster, it will know, and it will recommend toasters to you for the next week and a half. So that's some of the applications of what recommender systems can be used in. So now that we have a bit of a base, I would like to take you through the different parts of the presentation. I'm going to talk about the different game design techniques or game design principles first that motivated this idea. Then I'm going to talk about an action role-playing game, which a screenshot of which you can see here. And this is going to be used as a case study to let you know how to implement these machine learning algorithms in a game to recommend in-game content. And then I'm going to talk about some of the machine learning methods that we used to do that. I'm going to go through the pros and cons of all of them. I'm going to conclude with results and findings. And another spoiler here is that we were able to generate better gameplay experiences, and we were able to retain more players when we used machine learning algorithms as opposed to not using them. But more on that later. And yeah, so this talk is beginner friendly. I realized that I would have a mix of audience. So even though this research took about 2 years to shape up, but I'm going to keep at a really higher level. I'm going to just in a very like higher level and abstract way touch upon everything that there is to know, but I won't go into too much detail. So even if you don't have a programming or a mathematics background, you should still be able to create a tool for yourself, and then you can use that tool whenever you think is necessary or if it fits a particular application. So let's talk about some of the game design principles. This is a screenshot from Doom. So anyone knows the Doom game original that was really popular? So what's interesting about Doom is back when it came out, there wasn't a particular genre called first-person shooters. It hadn't been established as well as it now. And the funny thing is that even back then, the creators of Doom realized that everyone perceives difficulty in a very different way. What might be really hard for me might be really easy for you. So they had to do that. And a problem with this thing, even though it was way ahead of its time, is that I don't know what hurt me plenty means. I don't know what to expect the first time I'm playing this game. And a problem with that is when I go into the game and I realize that it's too difficult or too easy for me, most of the time I would need to restart and lose my progress. And of course, that was improved. Nowadays, you get a bit of a description with your difficulty setting, so you have a bit of an expectation what you might get when you get into the game. And sometimes games also let you change difficulty settings within the game. Second thing I'm going to focus on is player-tailored content, which is by no means a new concept. A lot of games do that in a very fun way, in a way that it's embedded into the game design itself. So for example, The Walking Dead by Telltale Games, if you don't know this game, it's heavily narrative driven, and you make choices, and based on your choices, you have outcomes that shape the story, and that keeps going. And this game and a lot of games like this use narrative and non-linear storytelling to shape the game and tailor it based on how you would want to play it. Mass Effect, if you know it, does the same thing as Walking Dead, but on top of that, lets you play a certain personality type. And even if you and your friend make the same choices, but if you are being badass and the other person is being really reasonable in the game, you would get a different type of gameplay experience. And let's talk about Left 4 Dead. If you don't know what that is, it's a zombie co-op shooter. Basically, you just shoot zombies and go to safe houses, and it just repeats after that. And what's interesting in Left 4 Dead and many games that are competitive is that it uses dynamic difficulty adjustment algorithm, which is an AI algorithm. This algorithm during runtime picks up if you're being too overwhelmed, and it will reduce the difficulty for you. And if you are standing there for a while, it will also recognize that and will throw in some encounters like a horde of zombies, so you feel challenged. And also sports games like FIFA also do that. It changes the difficulty as you go along, and that is based on the concept of flow, which comes from psychology. So it states that human beings like to work. We like to be challenged, and the challenge needs to be just right. It needs to be hard enough so you can overcome it and then get to the next one. If it's too difficult and you fail repeatedly, you will lose your interest and you will feel frustrated and you might give up whatever task you're doing. If it's too easy for you, you might feel bored and you might feel that it's not worth your time to keep on doing it. So this is a concept that I would be quoting again and again through the presentation. So this concludes basically the first part of the presentation, the game design principles. So we talked about adjusting difficulty according to what the player might like. And the concept of flow also is basically in everything in life. So a book is divided into chapters and each chapter builds upon the other one. So it's not something that only influences games or apps. Another thing that we discussed is generating your content towards the player. So now let's talk about the game that we are going to use as a case study. So it's based on the Troll Hunter series by Dreamworks. And this, if you haven't watched it, it's on Netflix and I would recommend it. The first season is a bit like it starts off and you would think that it's catered towards a younger audience, but it gets a bit darker as the series goes on. So if you're into animated series, I would recommend this one. So the game that we created was a single player hack and slash dungeon crawler role-playing game. And it's free to play and it's cross-platform HTML5, which means that it can run on any device that has a WebGL browser. So it can run on your phone, your tablet, or your desktop. It was created using Three.js and Phaser, which are JavaScript libraries. Not going to go into too much detail about that. And I think only the programmers here would be really interested in it. If you are, however, we can talk about it later. And I especially like to see if you're working with Three.js or Phaser. So the gameplay spans over 30 levels. It has 9 story quests and virtually infinite side quests. So I'm going to talk about virtually infinite side quests a bit later. Let's see how the game actually looks and how it plays out. So here's the core loop of the game. You start at the troll market, which is a non-combat zone, and you take a quest from an NPC. There are 3 NPCs at all times in the troll market. If you like the quest that you want to play, you can go to the dungeon. You always have an option to choose a quest between two options. And let's say you liked it. You went to the dungeon, you battled it out, you completed all of the phases of the quest, and once you're done with it, you can come back to the non-combat zone, the troll market, and you get a bit of XP. If you get enough XP, you level up. And once you level up, you can put your level in one of 3 attributes. So in strength, which is your hit points, your damage, or your agility. And this keeps on going after that. Whenever you play a couple of side quests, you get a story quest. A story quest is completely tailored and it's based on the series. Once you're done with that, you play a few more side quests and this keeps on going. Now at this point, let's talk about content a bit more. And then I'm going to tell you some of the parameters that we had while developing this game. So it has the following quest types. You can collect gems, you can fight enemies, you can fight a boss, and you can rescue lost friends. That's it, all of the quest phases laid out. And each quest can have either 1, 2, or 3 of these phases. Then you have 3 quest givers. So like I said, at one particular instance, you can choose between 2 quests and 2 of these 3 NPCs would be active. You have 5 types of enemies and their difficulty ranges from easier to the left to the hardest to the right. And you have 2 types of environments also based on the series. Now, this is the entirety of the game content. And this was also another work for hire. We don't own the IP, of course. Super RTL, which is a broadcasting network in Cologne, owns the IP, and they reached out to us to develop a game. And the conversation went something like this. Has anyone heard or played Diablo? All right, so quite a few people. Yeah, so what this said was, we want to make Diablo, but you have 3 months to do it, and you have this much budget to do it with, which meant that at a time only one developer, one artist, one animator would be working on it. So this is what we could come up with within 3 months. And of course, the content isn't really enough to have a lot of replayability, but you need replayability in free-to-play games. And to fix that, what we did was we used procedural content generation to generate more content with less amount of building blocks. So procedural content generation means that we give a seed value to a content generator, and it gives us a quest and a dungeon. So as input parameters, we put in seed and difficulty value. Seed could be any string. The difficulty value is equivalent to the level of your player. And as an output, we get a quest and a level. So by level, I mean a dungeon. And the procedural content generation algorithm, which I'm going to call PCG because procedural content generation is a mouthful. So the PCG, the first thing that it makes is the quest, and based on that quest, it picks up building blocks of the dungeon, and then it puts them together to create a maze-like structure. Then it can plant the enemies, the gems, everything into that maze-like dungeon and put the player at the start of it so the player can play it out. Now, at this point, we are not using any machine learning or smart algorithms to generate this content. And this is actually the first release of the game. This is what we gave the client as a first release, but it wasn't enough. And we thought that we could improve it by adding smart algorithms that could recognize, even in the context of this small amount of content, what the player might like, and more importantly, what difficulty the player might difficulty might suit the player better. So now let's go to the next part of the presentation, where I'm going to talk about the machine learning algorithms that come on top of this game. So we right now have our game client, and on the other thing that we added was a recommender server, which is in the cloud. None of the machine learning happens on the device itself. Whenever you complete a quest, you send player statistics to the recommender server. And whenever you want a quest, whenever the client or the player wants a quest, that quest is sent from the recommender server to the game client. It's not generated during runtime on the game client as it used to. So some of the features of the recommender system are it uses a basic client-server architecture. It uses Golang and Python for its development. It uses MariaDB for storage, which is an SQL-based database. And again, I'm not going to go into too much detail about that, but if you have a question, you can ask me after the end of the talk. Now let's go to the important stuff. How do we collect feedback? What do we track to develop a player profile? Because we already have quests and everything that there is to know about quests, but we need to collect enough granular data about the players so we can recommend them the right type of quests. So here's what we know about the quest itself, the environment, the NPC that offered it, the difficulty value, and the quest phases. And this is what we chiefly use for the player. The skill build, level strength, agility, and damage of the player, weapon accuracy, which means how many hits the player took and how many hits actually landed, the completion time of the quests, and the health lost, which means how many health packs the player collected in the dungeon and how much damage the player took from enemies. And lastly, the quest completion, which means whether the player completed a quest, whether the quest was failed and retried and retried and retried, how many times it was retried, whether it was abandoned. And an important learning that I would like to share here is that kids, and when I say kids, I'm talking about children ranging from age 5 to mid-teens. They have so much content to play with. They have so many different quests that they can play in this game, or they have so many games in general to play on the portal where this game is hosted, that they won't wait if they don't like something, they will just reject it. So if they don't like a quest, they will just abandon it and start a new one. So one of the challenges would be here to reduce the abandonment rate as well. So this is the 5 to 9 points are the feedback that we get from the player to create a player profile. And while we are on the topic of feedback, there are two types of feedback. Explicit feedback, so for example, Netflix asks you for a thumbs up or thumbs down. Amazon asks you for a rating of the product that you bought. And then there is implicit rating, which we exclusively used, which is we track the player behavior, how the player played a quest. And in our case, we couldn't use explicit feedback because that would have completely broken the illusion of the game. But again, I wanted to mention explicit feedback because the best thing would be to use both of these types of feedback. If your game can creatively ask for explicit feedback, I would say go for it, use both. So now let's talk about the machine learning algorithms themselves. So in a normal game that uses PCG, you could on the fly just give a seed, give a difficulty value, generate a quest, give the player that quest, and you're done. But in our case, since we need the recommender systems to know what different types of quests there are, what we do is we generate 90,000 quests right from the very beginning. And we give all of the information to the server that these are the quests that we're going to use, only these quests. These are the seed and the parameters of the quest, which we just talked about, and this is sort of the bubble that we would stay in. And 90,000 is a big number. It was enough from what we experimented. So now that you have these quests, then we have the machine learning algorithms. The first one is the content-based or the rule-based filtering algorithm, and the second one is collaborative filtering algorithm. And there are 3 different variations of collaborative filtering algorithm. So let's go through this one by one. Let's talk about content-based filtering first. So this is an easier one, and it takes the features and the difficulty separately. So one of the things that it tries to do is it sees what's the weapon accuracy of the player, what's the health lost of the player, what's the failure rate of the player, and based on that, it tries to adjust the difficulty. And now at this point, I said in the beginning that when you were using PCG algorithm, that difficulty value is equivalent to the player level. So if the player is at level 17, for example, the difficulty would be level also 17. But now in this part of our game, we do not have player level equivalent to difficulty because the player might not respond well to a particular difficulty. So player could have the same more or less difficulty than its level. So this is one of the things that it does based on the concept of flow. We change the difficulty value and prescribe those quests exclusively. Second thing it does, it tries to predict what the players like to play. So a player might like to collect things more than kill things. A player might like a particular NPC more just because that particular player established a connection with the NPC from the series. And there might be a certain face type the player enjoys more. So the way that we predict what type of quest features the player might respond better to is by taking ratio of the options. So whenever the player plays a game, we check which environment the player preferred playing, which quest phase the player preferred, which quest giver the player likes more. Now you might notice a problem at this point. What if we are wrong in our prediction? We will just keep going on with the prediction. And this is a very common problem in machine learning, and it's named overfitting. The way that we reduce overfitting in our case is 70% of the time, or 70% of the quests that we give to the player are what we predict. And 30% of those quests are completely at random. So even if we are wildly wrong in our prediction, the player can still nudge the recommender system to what might be the right predictions. So that was the first part of what the algorithm does. Secondly, what it does is it changes the difficulty value based on the player's skill. And we do that by using a piecewise linear function. So let's just look at one of those top 3 factors. Let's only look at weapon accuracy for now. So let's say we have our players, and the first thing that we do is across all of the players and across all of the quests that they have played, we take a global average of accuracy, which let's say in our case was 40%. And then we compared that accuracy to the accuracy of the player. So let's say our player in question had the average accuracy of 25%. So which means that the player is performing worse than the global average, which means that we need to reduce the difficulty of the player. We do that by putting those values on a piecewise linear function. So on the x-axis, you have all of the difficulty percentages. So from 0 to 100, our breakpoint is at 40 because our global average was at 40. So, and at the y-axis are the variation of difficulties. So from the graph, it's clear that if you have a player that has a higher accuracy average than 40%, we will increase the difficulty slightly. And if the player has a lower average value, we will reduce the difficulty slightly. And our player lies at that blue dot here, 25%, which means that we need to reduce the difficulty by 1 point. Now, this is an oversimplified view of what actually goes on. So I've only shown you an example of accuracy. We do the same for health loss and failure rate. And we use all of these 3 factors, the accuracy, the health loss, the failure rate, and we weight them to calculate how much of a change in difficulty level there should be. Another thing that I would like to mention is that I just went in and said 40% is the global average. There is a chance that might not work for your case. So you might need to go with a heuristic for that. You might think that 40% doesn't really accurately describe what the average accuracy should be, for example. And this is one of the limitations of the content-based method. So talking about its pros and cons, it's easy to formulate. It has, excuse me, it has a small runtime, and machine learning algorithms are notorious for having large runtimes and requiring very large amounts of space to make them work. But it needs to be tailor-made. So this solution will probably not work if your game isn't like this, if it isn't a combat game. It needs a lot of iterations. So every values might not work. You might need to go with heuristics. You might need to iterate over what the best values are for your game. And it can miss out on a lot of information. So in my opinion, I thought that those features that I went with, environment and NPC and face types, were all that I need to know, all I need to predict what the player might prefer. But there might be a dungeon that's shaped really nicely that the player likes, and the player might really like to play that sort of a dungeon again. There might be a dungeon that has a particular type of enemies that the player likes, and the player might like to fight against those enemies again. But this model doesn't really cater to any of that. So how do we improve that? The next algorithm I'm going to talk about is collaborative filtering. Now, before I talk about the actual game, I want to start with something small and then build our game on top of that, because it's a bit hard to explain. Well, not hard, but it takes a bit of a number of steps before it would become clear. So let's talk about the Netflix example again now. And let's assume that Netflix allows you to rate the movies from 1-star rating to 5-star ratings. So in essence, what collaborative filtering does and what its strength is, it plots a n-dimensional latent vector space, and it tries to put or categorize everything, all of the items which in case are movies, in that n-dimensional latent space. So a 2D simplified example of that is shown here. So your movie might be light action to violent action or childish to serious. And there might be a lot more different factors that go into that. You might like, for example, you might like exclusively horror movies, but you might also like every movie that Tom Hanks has been in. So that is a very complicated, like human beings are very complicated in their likes and dislikes. And collaborative filtering is really good at recognizing this. And the way it does that, and the word collaboration might give you a hint, it tries to put things together. It tries to put movies together. It tries to put users together. So an example of that is you create a movie club that talks about action movies. And since you are in that club, it's a good idea that if you were to recommend an action movie to another member of the club, that might be a good recommendation. And collaborative filtering does the same thing. It tries to group up players or users that might like a particular type of movie together. And then since they are together, then what one person might like, another person might also like. Now, this was all pretty theoretical, so let's see how this actually happens. So this is how your data is represented in collaborative filtering algorithms. On one axis, you have the users, and on the other axis, you have your movies. And everything that you see in the middle are the ratings of the movies. So let's compare two users together. Let's say user 1 really liked Lego Movie, really liked Expendables, didn't like Notebook. User 3 liked Lego Movie, didn't see Expendables, that's what the dashes represent, didn't like Notebook. So for collaborative filtering, it will get thinking that, all right, maybe user 1 and 3 are comparable since they like and dislike the same kinds of movie. So maybe it's a good idea to give a recommendation to user 3 about Expendables. And we could be right, we could be wrong. If we are right, then great, we won. If we are wrong, then we learned something. And the next time, the recommender system would have a better recommendation for user 3. And the way that we calculate the similarity of user 1 with user 3 is by using any similarity function. You can use Euclidean distance, cosine distance, nearest neighborhood, that's up to you. If all of these sound really foreign to you, let's just look at it this way. So user 1, so all of the users can be represented in terms of vectors. So a vector is sort of a line with components. If you recall the normal high school mathematics, and all of the ratings are components of those vectors. And what we see and what we try to calculate is, so if we have a user vector 1 and we have a user vector 3, we try to calculate the angle between those vectors and try to see how close they are. So this is cosine similarity, which we have used in our case. And even if you don't want to think too much about the math, just look at the right side of the equation. Their similarity value is 0.71. If it were 0, that would have meant that they were nothing alike. If it were 1, they would have been completely alike. 0.71 means that they are sort of alike, but yeah, this is a very small utility matrix. In reality, you would have a lot more users, a lot more movies, and you might be able to get better recommendations. So this is basically the extent of the implementation of collaborative filtering. Now let's move on to our example of using it in games. So we have our users, which are players, and instead of movies, we have our quests. And since we do not have explicit ratings, what we have is implicit data that we calculate. So in our case, the things that we create utility matrices with, and we use multiple utility matrices, is the level of the player, the strength attribute, the agility, damage, health lost, accuracy, and time duration. And we use 7 utility matrices to check the similarity of users with each other. Now, the only thing, now this isn't a matrix anymore, it's a tensor. Tensor is just a 3-dimensional matrix. So since we cannot have explicit rating, we need to do this. We need to understand how are the players alike in a variety of different ways. And this is all of it lined down. And what you might see here are the percentages in brackets behind, in front of every single factor, which means that we didn't just consider them in raw format, we weigh them. So level has the highest weightage of all. We try to group players together which have similar levels. And in the same way, at the bottom, we try to group players together that have the same health loss, who take the same amount of beating from enemies. So,
have you ever experimented with different ratios of those with machine learning and trying to get the best fit?
Yeah, this is something that also is a heuristic. You have to go through a few iterations to get that right. But the good thing about collaborative filtering is that even if you do not use these weightages, it will still give you good answers. And that's something that we actually started with, no weightages. And then we went on to add weightages later on. So yeah, that's a pretty good question. And collaborative filtering is good enough, it's smart enough to recognize all of these factors implicitly. So to conclude, the collaborative filtering algorithm, instead of movies, in our example, we have quests and our users that are in the n factor latent space. And the users that are together, that are close to each other, might like or might enjoy the same quests. So now I talked about one variation of collaborative filtering, which is dubbed as neighborhood filtering. And then to give you a bit of a summary, we constructed utility matrices, we computed cosine similarity, we weight the cosine similarity, we pick the users that are closer to each other, then we choose the quests. Now there is an empty box, and that's where the different variations of this algorithm come in. So in case of neighborhood filtering, we just do this and nothing else. And we have a second variation which is called the matrix factorization. And in that case, we have an extra step, SVD, or singular value decomposition. Now again, not going to too much detail about that because that's going into too much mathematics of it. But like in a very simplistic way, a way in which a mathematician would like to punch me, SVD just amplifies your latent factors. So it takes your utility matrices with the raw data, and then it converts it into, after this SVD step, into a really cryptic data, which you won't be able to understand, but the cosine similarity really benefits from. And in the third variation of the collaborative filtering algorithm, we use a different type of decomposition, and that's pretty much it. Dual decom, which instead of taking all of the matrices separately, it takes the whole tensor as a whole and decomposes it in one step. But even if you don't understand this, I just have this for completion because I'm going to show you results of all of these variations. So you don't really need to go into too much depth if you just want to get the idea of how it works. So a problem with collaborative filtering is, so the good thing about collaborative filtering is that it's applicable of a variety of scenarios. I gave you two examples, and if you get your data right, you can probably use that for pretty much anything that can be translated over a recommendation system. It can detect latent factors that we completely would have missed in our content-based algorithm, and it's low maintenance. The problems are it has a cold start problem, so you need to have a good amount of data before you can make good recommendations. So if your game has a very small niche and only like 100 players are going to play it, this isn't a good algorithm to go with. And it's resource intensive. So matrix multiplication and matrix arithmetic is pretty involved, and you need to do a lot of optimizations in that case. So let's get to the results. We use A/B testing. There is one control group that do not get quests from our smart algorithms. It just gets quests from a PCG algorithm, and the rest of the groups get quests from our smart algorithms. In this particular cohort, we have 25,000 players, and we just assign these groups randomly to players. So firstly, I'm going to talk about the quest failure rate, how that changed. So let's look at this graph and go through it one by one. So your baseline is your control group, and on the first one is your content-based algorithm that I talked about in the beginning. And as you can see, it reduced the quest failure by 22%. So that's quite a bit of improvement. And then you have 3 variations of collaborative filtering, which also did better than your control group. Secondly, we have the abandonment rate, which I talked about in the beginning. So your baseline is at the bottom, and the rest are content-based, showed an improvement. Collaborative filtering generally showed improvement, except the metric factorization, which didn't make a lot of difference. But yeah, in general, using the third technique, the tensor-based factorization, we can show a lot of improvement here. And the greatest statistic of them all, the retention rate. So a lot of data just for completion's sake, but just look at the last row. So you have your baseline or your control group at the first position there, which is 3.45. And as you go ahead, you see all of the collaborative filtering or the content-based filtering algorithms, all of them perform better than the baseline. We also went through 3 more cohorts just to make sure that these results weren't a fluke, and we were able to reproduce these every time. So to summarize, there is a need for better tailored content, and machine learning algorithms can be used to better identify player profiles. This is something that it offloads from the designer. It can tailor PCG content in a very smart way. And finally, the matrix and tensor-based approaches outperform the collaborative filtering, especially in terms of development time. It takes far less development time, and since there are far less iterations needed by collaborative filtering, I would always recommend using that. So if you want to go into in-depth detail about how these can be actually implemented, I published a paper with that. This game was developed by Flying Sheep Studios. RTL, which is a broadcasting studio in Cologne, Germany, funded this, and Fraunhofer Institute of Technology basically gave us the necessary advice to create these algorithms. And even if you don't want to remember the long name of the paper, you can just look it up on my website under my publication section. I only have 1 publication, so you won't get lost there. So, and yeah, that's my Twitter handle. I occasionally talk about machine learning and HTML5 game development. And yeah, I'd like to quickly add that some of the retention rates that you might have seen, like average of 3%, isn't huge. But just to make a case for using machine learning algorithms at a meta level in games, Rovio, which is the developer of Angry Birds, has recently done the same thing, and they use a different breed of machine learning algorithms. They use the one which is called reinforcement learning to basically do the same thing, present the levels to the players which are most suited to them based on what their difficulty level is. So this has definitely a lot of potential. Yeah, that's pretty much it. Thank you very much for coming. So we have 15 minutes till the next session starts. Let's take a few questions and we can, yep.
So I'm just wondering, the story quests, were those static difficulty or did those change as well?
Yeah, the difficulty level of the story quests changed, yeah.
So I'm just wondering if I am having trouble with a certain boss, can I just lose to it a bunch of times and that'll lower the difficulty so that I can beat it?
Yeah,
okay.
That will. Yeah, but that's how it's supposed to work. So if you're losing to a boss quite a bit, it will give you the illusion that, oh no, the boss is at the same difficulty level, but you are much better now. And I will like fake the difficulty reduction for you.
If that starts happening in real life, then write a paper about how this was all just a game.
Right. So, yeah, I mean, yeah. You have a question?
A different question, and you may or may not want to answer this, but you said 3 months to develop that one game.
Yeah.
Which is very quick, and your team consisted of a designer
So one designer or project manager, of course, then one developer, one artist, one animator. So 4 people in the core team. There were other team members as well. Some of them did sound, some of them worked on the balancing of the game, QA. I'm not including that. The core member were these 3 people who basically did all of the development.
And your budget, can you speak to that?
I actually have no idea about that because I am a developer. I don't really negotiate the budget details of the game. But yeah, if it surprises you that we I think did quite well for 3 months, even though the machine learning algorithm phase started after that. So that's after the 3 months that we spent developing the game. But we have developed so many games, and we have quite a bit of experience of going through these small life cycles that when we finally got to this one, we already had a lot of tools and a lot of stuff that we had already done, which we built on top of stuff that we could borrow from other code bases. So that's why the development time was possible. Yeah.
Similar to the first question, I'm just curious if you have anything in place to prevent or disincentivize player manipulation, like what the first question was asking about, where like players who are observant enough notice, like if I do poorly, I can rig the system and kind of breeze through the game, which makes the game boring, which means that they're going to stop playing it. Is there anything that you have in place, like quests that are more difficult or work better, or I'm just curious.
So one of the things that we did was we had a cap of how much difficulty would increase or reduce. And secondly, after every time you level up, that whole metric that what your difficulty is changes. So in our case, we did test on that, and we weren't really able to see if the player were getting anomalies in their difficulty predictions. But yeah, we didn't really explicitly check if someone was manipulating the game. But yeah, since again the life cycle of the games, since the kids would get to level 30 and then you see a very low retention of, like, the long tail is pretty low, you don't really feel worth it. But yeah, if your game has a higher player base, then that's something that you should check out. Thanks. Yeah.
With testing the different models, were you doing that after the 3 months of development, or during the 3 months? Like, how do you test different models while also?
So we released the game first without any machine learning algorithms. Then we started developing these algorithms one by one, and eventually when we had everything, this cohort of 25,000 players that you see is after the end of every algorithm being developed already in there, and then we tested it out. So 1, 2, 3 different cohorts, and then we were satisfied that, all right, yeah, this is working. Any other questions? All right, so I'll be hanging around if you want to, if you have other questions, if you have suggestions, if you have worked on something similar, I would really love to hear anything out. So thank you very much.
It's wonderful.
Thank you for
My name is
coming.
Mohammed. I would like to have, I don't know if you can share the presentation with me or you can't.
I think I can.
If you can, that's okay.
Yeah.
This is my card. I would like to have your card if you have it.
Yeah, of
And
course.
Also, I'm a professor of structural technology. We almost working in the same design and the same structure and the same infrastructure like you did,
All right.
but in education for learning courses, teaching. But the same using the machine learning, adaptivity, artificial intelligence, the same thing.
Yeah.
But we are professors. We don't develop anything by ourselves. Do you have any difficulties to work. We are from Arkansas. I'm here from Arkansas, United States.
Yeah.
So could we collaborate in something similar? Because it seems like our developer, this is what you do.
Yeah.
And if we build the content, for example, instead of graphics and all this, but we are working on something similar that we can test it as a prototype, that this prototype can actually be funded from the government. I mean, they are working to develop something like this for distance learning. And instead of the game, not but the content itself.
Yeah.
Like, for example, if you're going to teach math, we can make different levels of math difficulties
Yeah.
or physics, whatever.
Yeah,
the
exactly.
content, this is what we develop. I mean,
Yeah.
as a professor, we develop the content and with the assessment and everything you needed. We need to connect it with machine learning to adapt to the students learn. For example, learning styles. Some students
Yeah.
like to read. Some students like to kinesthetic, would like to touch.
Yeah.
Some students would like to be visuals.
Yeah.
And the machine learning will study their behavior, how they interact in the first few modules, and then it will develop the algorithm that can help them. The more they interact with the content, the more they will be able to succeed in the course.
Yeah.
So this is exactly what we're working on. I don't know how much you are free that you can, either your company, we are professors, we don't have much money actually, we don't have actually zero budget, but we can, if we can develop some kind of a small prototype
Yeah.
that can be applied here, we can get from the National Science Foundation, I mean, big funding for this, as a prototype of a course online, smart course to be adaptable to the students' learning.
Yeah, so what I can tell you is that as far as consulting is concerned, I think my company might provide it. Is something that I would need to ask them. So we have done this for ourselves once. We haven't really done this again or for any external client.
In university, I mean, there is no any educational, institution contacted you guys.
All right, no institution contacted us. I actually did this as a part of my master thesis. So for that research part of it, I went to the Fraunhofer Institute of Technology, which is the research institute that actually gave me advice on all of this.
Perfect.
So, but again, they were only for like once a month, 1 hour meeting. I had to do all of the engineering and all of the literature review.
That's right.
As you have to.
Absolutely.
So, I mean, as far as the engineering and development is concerned,
The company has to
the
decide.
company has to decide on that. I don't really have any say. I can just say that yes, this is something that's interesting and that's something that we should do, and But as far as the consulting, that might be a bit more possible. But again, I would have to
check with them
check with
first.
my superiors.
Do you want me to remind you, contact you?
I want you to email me. Yeah, definitely.
Officially, okay,
Yeah.
and then you can actually tell
Then
us.
I can
Because
discuss. Yeah.
like I said, this infrastructure, the
Yeah.
same 100%, this is exactly what we brainstorm, and we have some kind of blueprint, but nothing done yet.
Yeah.
By the way, my master's degree is from Munich University. I studied in Germany 6 years, so
okay.
I traveled to Germany and I know the college. So I'm proud of you that you be there, successful and work. It's difficult to work with German. I mean, somebody lived there and here. It's like, I mean, they are, but you're smart enough. Thank you so much.
Thank you
Raheel.
so much.
Thank you, sir. Thank you.
Hi, Raheel. I'm Lester. Very informative. Really appreciate it. Let me ask you this. Are there any opportunities